what Snell's law says is that when there is a change of medium that a light beam is passing through, then there could be a bending of the light ray at that boundary. And so what we want to do here is use this relationship, Snell's law. It says n1 sine of theta 1 equals n2 sine of theta 2. All right, so first of all, we have to talk about what n is. N is an index of refraction and it's going to just depend on the medium that the light is traveling in. For a vacuum, n is 1. And for air, n is just about 1 as well. So we'll assume that n is approximately 1 for air because it's not very dense of a medium. And when it comes to light speed, it's just pretty similar to the speed in a vacuum. Now, n is 1 for air, but it says here that oil has an n of 1.4. Now, water has its own n as well. They didn't tell us what water's n is. N is 1.333 for water. All right, so what ends up happening is light travels at different speeds in all these different media. And it's going to travel with speed approximately equal to c in air. And c, as we showed before, was 3 times 10 to the 8th meters per second, and that's in air. All right, but the speed is going to be different in oil. And one way of reasoning out, like, why does the light bend, at that boundary? So here's one explanation for it, right? You've got your boundary, and you have a wave coming at an angle into that boundary, right? So you might have something like that. And so some say that when the wave is oscillating, that the boundary has to match up. Okay, and according to the formula, C equals lambda times F. See, if you were to analyze this, it would have a certain frequency of oscillation, right? But then when you get to the new medium, now you have V equals lambda F. All right, but the frequency has to remain constant is the idea, And so in order for that to happen, the thing has to bend so that there can be continuity of the wave form, because they always have to match up as they're oscillating. So if your speed goes down, then what ends up happening, in order for the frequency to remain the same, is that the wavelength has to go up in a new medium. It just causes the thing to bend so that can happen. Anyways, let's plug in the n's for the first transition, right? So we're going to use n1 for air, and then we'll do n2 can be the oil. Now, the theta 2 is going to be this angle here. Because in Snell's law, we always want to measure the angles relative to a normal. So the normal is perpendicular to the surface. So this is a 90-degree angle there. So the theta that it's coming in at is called the incident angle, sometimes written as like theta I, or perhaps in this case theta 1. And then the angle that it bends with will be the refracted angle. They say that the light beam makes a 20-degree angle with the normal line NN prime. Okay, so that's an interesting problem. They're doing a little bit different. They're giving you the theta 2 and asking us for the theta 1. A lot of times it's the opposite, but that's fine. All right, so we know that theta 1 is unknown. Theta 2 is 20 degrees. Because they gave us this one is 20, so that would mean that this one's also 20 by alternate interior angles. All right, so let's plug in. All right, solving that, we have to use the arc sine of 1.4 sine 20. All right, I get that theta 1 is 28.6 degrees. So, as you can see, theta 1 is bigger than theta 2. And that'll always happen. When you go from a smaller n to a larger n, your beam is going to bend more toward the normal. It's going to become a less extreme angle. So for theta, we'll put 28.6 degrees. Now they're also asking us for the theta prime, which is this angle down here. There's a transition between oil and water. So we want to use Snell's law again. But this time, let's use N3 to stand for the water. Then we can write it as N2 sine theta 2 equals N3 sine theta 3. So you could do this for any boundary. All right, so N2 is 1.4. And theta 2 is 20 degrees. And 3 is going to be 1.333. And then we can solve for this theta prime, which I'm calling theta 3. All right, I'm getting theta 3 is 21.1 degrees.